University College London, talking about the Quenches entanglement spectrum and irreversible working quantum theory.
Okay, thank you. Let me start by thanking the organizers for the invitation. So Vladimir, he is not here. Bruno, thanks, and also Chris. Thanks. Okay, and I'm going to speak about a lot of stuff which we will do on quantum impurity models. We will compute some measures of entanglement, and we will do Quenches dynamics on that. Okay, also see how it can be used to set up long-range entanglement and all these things. Okay, so just because Vladimir was not there, I already thanked the organizers, including you. Yeah. Okay. Now I have to put up this slide because I got into this topic of impurity models because of this person, Pasquale Sodano, who is actually now in quite a grave situation, as I understand, after a stroke in Brazil. So if I had not met him by chance in a conference in 2008, I was still doing these kinds of things. Okay, maybe irreversible work was still not kind of there, but some Quenches, some entanglement studies on generic spin chains, and it was the chance meeting with Pasquale in a conference in Perimeter in 2008 that got me into these impurity models. Okay, and they have kind of very nice behavior under Quenches and also how entanglement scales. So we have done a series of work on that. It's all because of Pasquale, who I don't know whether he will recover. I hope he will recover, but we keep our fingers crossed. Okay. Okay. So the typical, the most famous impurity model historically is the Kondo model. Yeah. And as you can see, it is a model where you have a spin embedded in a solid, and there's a screening cloud over length xi k, which people call the Kondo screening length, where all the mobile electrons in the solid, they screen the spin of this impurity. Okay, and this kind of screening cloud lasts up to a temperature Tk. Okay, so there's this length scale xi associated temperature scale Tsk, despite the fact that it is a gapless system. Okay, so the Kondo system is kind of a unique system in the sense that it is gapless. I mean, a lot have been said about gapless systems in this conference, yet it has a length scale defined by the screening cloud. Okay, so it has a unique situation. Okay. And of course, this model historically, of course, very famous model. So aside Kondo and Anderson, so it was solved by Wilson and then also by Bethe-Ansatz later on by Andre and Wigman. So it's a very famous model of condensed matter physics. Okay. And it also has realization more recently in artificial structures, where particularly a quantum dot spin. If you have a single spin in a quantum dot, that can act as an impurity, which is screened by spins of electrons in leads attached to it. And that kind of thing can provide a fertile ground for quantum technologies. Okay, so as I'll show at some point later on, how non-equilibrium dynamics, which you can induce by Quenches, can actually also be used for long distance entanglement through these models. And that kind of thing would probably have application in these artificial realizations of Kondo. Okay. Okay. So let me set the scene by what I will work with. Okay. All the work I have done, we have done with lots of collaborators, and primarily has been mainly carried out by Abul Fazal Bayat through numerical DMRG. So most of the work, so all the work is numerical. Okay, though at the end now we have some interpretations of the things that will come at the very end of the talk. But to do numerics and DMRG, you need a convenient model. Okay, the Kondo model that I showed, the 3D model, okay, is of course can be mapped to a semi-infinite model to start with, okay. Even the original Kondo model, which one can call free electron Kondo model, okay, because the origin is taken at the end of the line, and you assume S-wave scattering, okay, so that you can really convert the 3D to a 1D, okay, with the impurity at the end, okay. The other thing to realize is that the most important physics of the Kondo model is the screening of the impurity spin by the spins of the itinerant electrons around, okay. So it makes sense to retain only the spin sector of the model, okay. So you can gap out the charge sector, okay, which makes it at half filling will make it a Heisenberg chain, okay. And that is a model which was introduced by Ian Affleck and co-workers, so particularly Eric Sorensen and Nicola LaFlorenzi, where you take a spin chain, okay, and at the very end of this spin chain you have a spin which is coupled with slightly different strength, J dashed, okay. This is called a Kondo spin chain, okay. Of course there's no charge here, okay, so it's only the spin sector, and it reproduces the low energy behavior of the spin sector very well, okay. Of the Kondo has the same low energy behavior as the original free electron Kondo model, okay. Deliberately also a next nearest neighbor coupling is introduced in the spin chain. The spin chain in some sense is replacing the bulk here, what would be the leads, okay, and this impurity spin, this spin with slightly less couple is like what would have been the impurity spin in a solid, could be like an isolated spin in a quantum dot, okay, and this spin chain is representing the bulk, which would have been the leads, okay. And deliberately also a next nearest neighbor coupling J2 is introduced here, okay, so that for two reasons actually, okay. So one reason is we have a good handle then to make this lead, okay, gapless or gapped, okay, as you might know, but let me tell it. So if you just take a 1D Heisenberg spin chain, okay, with both J1 and J2 interactions, then it is known that below a certain value of J2, the Heisenberg chain is in a gapless phase, okay, which is like the original Kondo model. The free electrons are of course a gapless system to which this impurity couples and can make this cloud, okay, can emerge this cloud. On the other hand, if J2 in this lead is larger than a J2 critical, then we know that the spin chain enters a gapped phase, and then the Kondo cloud cannot form, okay. So there are no states at zero energy for this very low coupling to hybridize and form a Kondo cloud with, okay. So this J2, having this J2 in the model gives us a nice handle to switch the system between a phase where we expect a Kondo screening cloud, which is below this J2 critical, and a phase after J2 where we do not expect a Kondo cloud to be screening the system. Yeah. Mm-hmm.
So here you are not considering the charge part, right?
No, charge part has been just gapped out. Yeah.
So when you say the low
only the spin sector.
Oh, the spin sector.
Yeah. Yeah. The charge sector is just a model at half filling in this case. Okay. This does. Yeah.
Means XXX has this scalar product of sigma.
Yeah. Sigma dot sigma is isotropic Heisenberg. Yeah. XXX chain. Yeah. So yeah, delta equal to 1, whatever. So where was I? Yeah. So one important consequence of that actually that this is actually slightly a different model. Okay, at all values of J2 less than other than the J2 critical, there is a slightly different scaling of the Kondo cloud. Okay, it's still exponential scaling with the Kondo coupling, but the length of the cloud still has an exponential scaling, but there's a square root, extra square root. And when you exactly have J2 equal to J2 critical, then that becomes exactly the same scaling as the, as the free electron quantum model. Okay, so these are two reasons why we use this extra J2. Okay, so what do we expect a priori? Okay, let us see what we expect a priori. Okay, so let us we will. Okay, so we know the screening cloud, yet it's a Heisenberg model. Okay, of course. So the impurity spin can point anyway, and always the bulk has the collection of spins have to screen that moment. So it has to be a singlet. Okay, and of course through RG people have shown that when you come to very low energies, this coupling becomes very strong. The whole bulk becomes like one spin which screens this. Yeah, but of course when the coupling is not unity, okay, and other things cannot be ignored, this cloud starts to become longer and longer, okay, as you go to finite couplings, and there's this screening length. So we would expect the impurity and this cloud to have to be forming this effective singlet, okay. As we'll show, this actually it's entirely not true. It can form many possible singlets, and so let me come to that later. But we expect this to form a maximally entangled state, this cloud to form a maximally entangled state with this impurity spin. Okay, and there's still a rest of the system. Okay, so what we expect, so if we divide the system into two parts, okay, so L is length of part A, okay, and capital N says the total length, okay, then we expect that when L is less than the cloud, then entanglement of the impurity spin S with A, okay, is less than 1. It becomes 1 when it reaches here, and then it continues to be 1. Okay, one can also think in the other way. Okay, the entanglement of the impurity with the B. Okay, so that is when this is very small, most of the entanglement of this impurity spin is with the bulk. Okay, so it's greater than 0. When it reaches up to this point, all the entanglement of the impurity is with the cloud, so the entanglement with the bulk goes to 0, and it remains 0 when you make the length larger. Okay, so this is just using the monogamy of entanglement. I should say we always work with even chains. Okay, so this impurity is one spin, and this is an odd spin lead, okay, so that we always have a total singlet, okay, so that by simple entanglement monogamy, this impurity has at most one unit of entanglement, okay, so to share between this and that, okay, and it shares it completely with the cloud, not with anything else. Yeah. Mm-hmm. Okay, alpha is just a constant. It's not, I cannot remember it or find it. In our cases, we always extracted the alpha numerically, but there are some predictions from RG as well on the model. Okay, and this is the scaling, expected scaling of the Kondo cloud length in these models as comes from RG. This root is the difference from the usual free electron Kondo model. Okay, so free electron Kondo model, the length of the screening cloud is alpha by j dashed, some other alpha by j, and here because in the spin chain model it is alpha by root j dashed. So it's a difference which is not qualitatively a big thing. So there is also this cloud and everything, and at the J2 critical it becomes alpha by j dashed. Okay. Okay.
You wouldn't expect there to be some exponential scale.
Right. Okay. So that's that's important. But there is this picture in some sense is slightly misleading. Okay. So this is the cloud is always tailing off. So what I mean by 0 is 0 in the sense of 0.01 or 0.001. So I don't now exactly remember what was the 0 in the numerics which Bayat did, but yeah. So we fix a threshold value of entanglement below which we regard it as 0. Okay. However, what does computing this entanglement involve? Okay, so you want to compute the entanglement of this impurity spin with this part of this chain. Okay, so you will have to trace out a part of this chain, right? Okay, so that involves calculation of entanglement of a mixed state. fundamentally of a mixed state. Okay, so this is what makes the usage of von Neumann entropy, which has been used extensively, not applicable here if you want to have a measure of entanglement. Okay, having said that, to give the people who came up this model, Affleck and co-workers, they also tried to probe the entanglement structure using a clever way, where they took the entanglement of a system without the impurity, then added the impurity, and took the difference. Okay, that's how they saw the effect of the impurity. Okay, this is called the impurity entanglement entropy. But that is not a bona fide measure of entanglement. Okay, so that is not a measure which will be unchanged under local actions and classical communication. Okay, so this is why we would like to use a bona fide measure of entanglement. Okay, yeah. So I mean, a lot has been said in this workshop already, so I don't know how much I will recap. Okay, but I have a few recap slides. I will go through them fast. Okay. So first of all, just even for later use, this is very basic, that what is our unit of currency for entanglement. Okay, so what is the $1 for entanglement is this kind of state of 2 qubits. Okay, 0, 0 plus 1, 1. Okay, why we regard it as the dollar for entanglement is that you can teleport one state of 1 qubit if you have that. Okay, and what is the application of that essentially is that to scale quantum computers. If you have several quantum registers, to connect them, you need this 1 EBIT. Okay, so this is like the dollar for the entanglement. Okay, and this is a pure state, so the von Neumann entropy is 1. That measures the entanglement. We call it 1 EBIT. Okay, this was coined by Bennett and others long time ago. Okay, 1 EBIT. And just to give an example, when you have these coefficients unbalanced, this is 0.9. This is like a 90 cent, okay, 91 cent thing. Okay, so you need many of those. So I think Frank went a little bit into describing that, but I don't have enough time. So if you take a lot of such things, you can convert to a ratio where 90% you can convert by local actions to dollars. Okay, so this is called entanglement distillation, and that's why it's important to measure entanglement. Okay, so how useful it is one way to measure. And of course, if the whole state is pure, as in both these examples, these 2 qubits are together in a pure state. Okay, and even true when you have a spin chain and you just half it. Okay, is that you can use the von Neumann entropy of a subsystem. Okay, so you take the reduced density matrix and the subsystem. The von Neumann entropy has been shown to be a good measure of entanglement, and it is indeed tells you how much of $1 you can get from a large collection of coins. Okay, by local actions. Okay. And as also has been touched upon, for a long time people have been studying the entanglement of one block with the rest through this von Neumann entropy of a spin chain, just because the whole thing is pure. So you can do that. You can take a block and you can just compute the von Neumann entropy. So for non-critical systems, we typically know it is constant. Okay, for 1D critical systems, there's this logarithm. Okay, so one of our organizers have done one of the early calculations using Bethe-Ansatz. Also, I think historically goes actually yesterday was I think it goes back to Sorkin, as I heard in Brazil last year. But then 81 or 83. I mean, it's before. We'll check. I don't know the paper. Okay, yeah, we can. Actually, he has a new archive showing his publication on. Yeah, so you can check that. So I think Sorkin probably did using harmonic lattices, and this was Wilczek was CFT. Within our community, Vidal and Rico and Kitaev, they did some using free fermion chains in 2003. Then was your calculation. Then was the CFT of Calabrese-Riccardi. Okay, so there's lots of results in that direction. Okay. Okay, so we have a situation now, as in the picture I drew, where we want an entanglement between something and something else, but we have a part we want to trace out. Okay, so A and B. Okay, so we want entanglement between non-complementary blocks. Okay, in my situation, one of these is a single spin, the other is part of a cloud, and the other is the rest of the system. Okay, but we still have a situation where we want to compute the entanglement between two entities which are part of a mixed state. Okay, and then as Zoltan highlighted in his talk quite a lot, that of course there are quite a few measures of mixed state entanglement, but none of them are easy except one, okay, which is the negativity. Okay, well, why easy? I won't say easy. That is hugely, underestimating the thing. But for simple systems, it can be easy. Okay. Okay. So just a recap on mixed state entanglement. So mixed state entanglement is defined starting to define what is not entangled, okay, and then all the rest is entangled. Okay, what we regard as not entangled is these separable states which Alice and Bob can prepare by just calling each other up and tossing coins. Okay, so by tossing coin, Alice prepares a up, Bob prepares a up, down, Bob prepares a down. So you do not send any quantum states towards each other, or you do not allow actually a quantum interaction between the states. Then the kinds of states you can build up are called classically correlated. Okay, so are called not entangled. Okay, I wouldn't go to classical correlated, but not entangled. Okay, that's the best way to say it. Okay, and because discord you can probably create without a quantum interaction. Okay, but so these are states which are not entangled. So the states which are entangled are those which you cannot create this way. So those states which necessarily require the systems to be interacted through a quantum Hamiltonian sometime in the history, okay, are entangled states. Okay, otherwise you don't have entanglement. Okay, and originally, there were lots of measures involving distances from separable states, which Vlatko and others did, and lots of other measures, but all are difficult to compute, okay, for general high-dimensional states. Okay, for 2 qubits, there's a very good measure in which I guess Luigi and others used originally for their quantum phase transition work. So that measure I will not touch upon, the concurrence, which can measure entanglement of 2 spins, okay, in a mixed state. But I will go to this negativity, and I mean, Zoltan already showed, so maybe I spend less time. You take partial transposition of one part of the system, okay, and the property of partial transposition is that it's not necessarily the output, the state that happens from partial transposing, say, just the B part, is still a density matrix. So it can have negative eigenvalues, okay. And the sum of the negative eigenvalues, so kind of intuitively more negative the eigenvalue is, it's more entangled. Okay, then people have also proved the fact rigorously that if you take all the negative eigenvalues, okay, and sum them up, then this 2 is just to make this unit, that the singlet has unit entanglement, then this is a good measure of entanglement. Okay, good measure of entanglement in the sense that Alice and Bob, by no matter how much coin tossing they do and how much calling each other they do, they can never increase this entity. Okay, so this is then a good. So what is a good measure of bona fide measure of entanglement is an entity you cannot increase without a quantum interaction. Okay, so that's what is. So this is then the negativity, and also negativity has a history which is which a lot of people came up at the same time. My good colleague in quantum optics, Myung-Sik Kim, he actually used it for continuous variable, the p to minus p, very early on in one of his works. Okay, Jens always claims it was all there in his PhD thesis. Yeah, and I believe so. I have, during his PhD, I think I saw some things that he wrote. Okay, now of course this was a paper, the Vidal-Werner paper really proved things. Okay, that and I think they proved that this was an entanglement monotone for the first time. That is a non-increasing. So it's a bona fide measure of entanglement, and Martin Plenio proved it also for the logarithmic one. Okay, the negativity itself, I think, is probably not additive, while the logarithmic negativity is. There is something there. Okay, okay, I don't go into that. Okay, but why is it, though it's a mixed state entanglement, and unlike the von Neumann entropy, it doesn't have this strong interpretation of the currency, it still forms bounds. So it, for example, if you are to teleport with a state, it gives you an upper bound, okay, the best you can teleport with something, okay. So anyway, I think negativity is well motivated by now, so I can proceed, okay. So this is back to the picture, okay, that we had, okay. Right, okay. So what we did is we computed the entanglement of the spin with actually the block B. Okay, the entanglement of the spin with the block B. Okay, this is just a matter of convenience that in the numerics it was with the existing code in the group, it was more convenient to do that entanglement rather than directly this entanglement. So we computed the entanglement of the impurity with the block B rather than with the block A. Okay, but you know that is by monogamy they are quite, you know, related to each other. Okay, so as the length grows, we see that indeed you can verify this exponential dependence, okay, this alpha by root, this exponential dependence with L. Okay, so here the J dashed is fixed, but the entanglement exponentially goes down, okay, with the far away part. Okay, and also another thing important here is, so this verifies the scaling we expect, okay, of the screening cloud, but also you see, once given the model, our computation is like blind, right? We are just computing the negativity of blocks, okay? We are not a priori taking any scaling or anything which we know from RG into account, okay? So we are just blindly doing. So what we will find can be called like an entanglement healing length, okay? So this entanglement is fully covered up to, becomes 0 up to that length. What is strange that this entanglement healing length has the same scaling as Kondo. Yeah. Yeah, this is the DMRG. These are, yeah. These are static ground states. So can be done. Yeah. Okay.
What's the Kondo screening length in this?
So this comes back to you know, Robert's question. So I don't remember. So one would probably take something like, you know, maybe 10 to the power minus 3. Yeah. So yeah, it is. You have to make a decision. This is the full length of the. No, the full length is 240. Yeah, you can take it there as well. So it's up to your. But what you take, you go on taking the same, you know, same measure to be 0 consistently in all your calculation. Yeah. Yeah. You have to stop it. Exactly. Yeah. So whatever you take as your unit of cutoff, you just consistently maintain it. Yeah. It is never becoming exactly 0. Yeah. Okay. So now, what do we expect? Okay. What do we expect? Now this is something which we expect a priori. Let us see whether that turns out to be true. Okay, a priori we expect that when you are in the Kondo regime, so when this bulk is gapless, okay, then a Kondo cloud will be set up and everything should scale. All entanglement properties should scale just by these ratios. The total length is to the Kondo length, okay, and the total and the length of your block to the n. Okay, so everything should just be in terms of the Kondo length, okay, and nothing else. Okay. On the other hand, if you actually set up a gap in your bulk, okay, then there's not this scaling behavior with the Kondo length. Okay, this is what we a priori expect. Okay, and this is what we see with respect to this entanglement healing length. Okay, so this gives us more confidence that we can regard this entanglement healing length as the Kondo length, at least in samples where you have a large environment after the Kondo length. Okay, so it's the total length is much larger than the Kondo length. Okay, and then the other thing we see is, so that how do we see that? That we see by taking different lengths keeping the same ratio. Okay, so we take we find out the Kondo length according to a criteria that after 0.01 or 0.001, where we make the total length 4 times of it, okay, and then the curves for different J dash directly fall on each other, okay, in the Kondo regime, okay. In the dimer regime, they are different, okay. So which means in the dimer regime, this entanglement is not following this, Kondo physics, okay. The entanglement is not scaling with the Kondo length, okay. It depends on the details of the system. On the other hand, there's very nice scaling behavior when you are in the Kondo regime, okay. Okay. This is at J2 critical, this is at J2 0, okay. And this is again, this is the scaling of the Kondo length that we find from this as the entanglement, healing length. Okay. So, yeah.
In the dimer phase, wouldn't one expect that N just drops out?
The problem is that this coupling with the N is not very strong, is very weak. Okay, it's still like a Kondo coupling, an impurity coupling. So if it was an open dimer, that would be the strongest. Okay, here something like that will happen, but it's still, less than full because this coupling, though it's an open end, is weaker than that one. So it cannot have these alternating strong, weak, strong, weak, strong, weak bonds. So it kind of has a bit more stretch, okay, but it doesn't scale or anything, okay. On the other hand, the Kondo scales. Okay. Now, kind of a simplified cartoon picture of the thing that you can come up with all this analysis is that this spin, though the whole thing will be in a mixed state, okay, whole thing has to be in a mixed state because there's a lot of entropy across this cut, across the system. You consider now system, cloud, and rest of the system. There's a huge amount of entanglement in the free electron model, or in this case the Heisenberg model, okay. There's this log n entropy, okay. So you cannot think of this as a pure singlet. Okay. So RG of course gives you a pure singlet, okay. Of course it doesn't talk about purity, but it gives us the singlet. It gives a Hamiltonian with singlet is the eigenstate, okay. But truly what is happening is, of course, there are many possible singlets you can form, because although with this spin you are just the option of up and down, the bulk has lots of ways of creating a down spin, right? So there are lots of singlets you form, and effectively you should be having kind of log n possible ways of doing singlets, which kind of are entangled with the rest of the bulk, okay. So it is the kind of basic cartoon picture that you can think of, from not just from our analysis, but also from the extra fact that there's a lot of entropy from the cloud part to the rest, just the entropy of log n of the thing, yeah, which you cannot ignore. Now, the question is, what about an application of this? Okay, how can we use it? Okay, now to use it in an application, we have to kind of go beyond the usual regimes which are interesting in condensed matter, or regimes in which you are safe to draw parallels between our analysis and what is known from RG, okay, or CF boundary CFT, okay. So you go to a regime where actually you have a good application. You go to a regime where you kill off this RG, okay. So the chain, you take a chain as a finite chain where you have, what happens is, as you lower this impurity coupling, you see this alpha by root J, the Kondo class becomes larger. Further lower, the Kondo class becomes larger. So you can go to a regime where the Kondo cloud touches the other end, okay. This is not a regime where you can expect analysis of scaling from RG or from CFT known before to be valid, because this is a system where the cloud is occupying the whole bath or whole lead, okay. But nonetheless, that is a regime very useful, okay, for dynamics. And before going to that, let me tell you a simple undergraduate textbook dynamics, which one can, or you can, it's easy to just calculate and check up. Say if you had two singlets, for example, okay, and at any time you coupled two of the spins in the middle, by a Heisenberg coupling, then after some time there would be the spins at the two ends would become maximally entangled. Okay, this is a 4-spin simply solvable problem. You can just do it will oscillate with time. Okay, just as usual dynamics. Okay, now one can then see whether you can stretch it to longer distances. Okay, we want these singlets, but we want the singlet to with over a longer distance. Okay, and this is where the Kondo will help us. Okay, so rather than this picture, I think this picture makes okay. So so this is what I was telling before. The Kondo is an extended singlet. Yeah, why is an extended singlet? Because you can make this J dashed weaker and weaker, so that the whole spin chain now is required to screen this. Is the one which forms the singlet. Okay, with this. Okay, unit entanglement with this. Okay, so if you arrange that scenario, then what is interesting is that you can really use this to replace these small singlets that I showed. Okay, the textbook singlets that I showed, 4-spin problem. Okay, obviously we will no use for large distances, but by making a weaker J dash and having a Kondo cloud is like a stretched arm, and you join them. Okay, and then this is the scenario. Okay, you have two Kondo spin chains. Okay, arranged of course in a very special situation where the Kondo cloud covers almost the rest of the full touches the end of the lead. Okay, okay. So here this length we are still continuing to call it the Kondo length, but you can also call it the entanglement healing length. Okay, and then at time t equal to 0, you just connect this with a Jm. Okay, and same dynamics takes place. Okay, of course now we are talking about dynamics, so we have to do time dependent DMRG, and in these systems it is a bit limited because of the the entropy changes in the bulk itself is quite a lot. Okay, can go from log n to n and things like that. But however, we are interested in one unit of entanglement growing, so maybe there's another way of doing it more efficiently. We don't know, but we did it just with brute forced time dependent DMRG, and you see the entanglement between the first and the last spin grow as blips, blips quite regular intervals, and at least up to the length of 40, it seems that it is going to a distance independent value. Okay, we do not have we do not have analytic evidence, but we have good logic to think why it will go to a distance independent value. Yeah, I'll tell you later. But this seems to be going to a distance independent value, and the time of course is growing with n. Okay, if it was not growing with n, it would be very strange. Okay, so you require some time for the entanglement to propagate. So this is the scenario. So distance independent entanglement means very good. You can no matter however your distance between two quantum dots, if you have two leads, okay, just connect the leads at time t equal to 0. If the leads are longer, you couple the dot weaker with the lead. Okay, we haven't done the calculation for free electron Kondo model, so I'm not know whether literally this is true, but it is true if there was a Heisenberg spin chain. Okay, for actual free electron leads, it's likely that similar thing will be true, but we have to calculate. Okay, now since we make the cloud touch the whole chain, you see we if we believe still in the scaling dynamics, then somehow the Kondo length is same as the total length, so you see that drops out, and you just have a time growing with n and the entanglement happening. Okay. So this is why this is how we justify the distance independent entanglement. Okay, and the optimal value of Jm has to grow. So I'm not going into these details. It's length of the chain. Okay, so let me skip over this. Okay, let me also skip over this. So the point is that when you have long chains, this J is like unity, same as the couplings inside the chain. Okay, that you enjoy. It's a function which is how the J grows. It comes from how this J dashed becomes weaker to cover the length. Okay, important here, why this phenomena is really using the Kondo cloud, that you can prove by using this tuning handle of the J2 to put the bulk in this dimer phase. Okay, in the dimer phase we will soon see that the entanglement between distant spins becomes extremely low, okay, while for the Kondo phase they seem to be kind of going to a constant. Okay. Okay, so this is the entanglement router, okay, that you connect any two parties by their extended singlets. What? Topo? No.
No?
Nothing topological here, no.
There is a model which calls topological Kondo. It has several wires coming.
No, it's not, yeah, it's not topological Kondo, no. That would be the other way round, and there would be, these three will not be spins. They would be three Majorana fermions. Yeah. So okay. Now, we also delved a lot of time on the reverse of the model that I was speaking so far about. Okay, so I was talking about the spin stretched cloud connecting, but you can just swap the thing back to front. Okay, you have and connect these with a coupling K. Okay, since there's no direct coupling term between the leads, okay, what this emulates is the two impurity Kondo model. Okay, so there are two channels but also two impurities, so this is called the two impurity Kondo model. Okay, and this two impurity Kondo model has what is called a boundary quantum phase transition. Okay, so bulk quantum phase transitions, as you know, I think Luigi was elaborated on that. So there is an order parameter which has a sharp change in value. Yeah. On the other hand, this boundary quantum phase transition, just one coupling changes the behavior of the whole system. Okay, the phase of the whole system. Okay, and the problem with many of these, at least the one I will speak about, boundary quantum phase transition, is that there's no obvious change in order parameter. Okay, the state is also before and after the phase transition is a SU2 invariant state. It's just that the entanglement structure gets redistributed. Okay, so it's important to try to find an order parameter for these things. Okay, but of course it's not an order parameter in the Landau-Ginzburg sense. Okay, it's something which is non-vanishing on one side and vanishing on the other side, plus scales with critical exponents. Okay, so this is what we are aiming for. Okay, just to quickly recap this model. Okay, originally I think maybe the first paper was by Krishnamurthy, Wilkins, Jayaprakash, but also Jones and Verma, also Affleck and Ludwig have worked a lot on that. But these are the two phases. So you have two separate Kondo things. Okay, so when the coupling between the impurity spins is very weak, they are screened by their individual clouds. Okay, and that is one phase because it's just that the origin is gone. Okay, so this becomes Fermi leads without the origin. Okay, in the other case, when there's a very strong coupling, okay, they just drop out. Okay, so there's no impurities. This just becomes a welded, this becomes a Fermi gas without seeing the impurities. Okay, and these two phases are separated by a quantum phase transition. Okay, so that has been proved in these things already. Okay, however, as you can see, everything is always isotropic Heisenberg. Okay, it's not easy to identify any order parameter which is changing, okay, across the quantum phase transition. Okay, what helps a lot here is this blind, again, a kind of, you can say it's a blind order parameter. You can try to compute it in many models. It's called the Schmidt gap. Okay, it comes from the entanglement spectrum. Okay, you take the difference of the first two Schmidt values. Okay, and people have shown that in the usual bulk quantum phase transition, the quantumizing model, it has a very nice scaling, this Schmidt gap. Okay, it acts as an order parameter. Of course, for that model, you have this magnetization as an order parameter as well. Okay, so we wondered whether this Schmidt gap would apply to a transition where we don't know of an order parameter. Okay, and indeed we try to apply it to this two impurity Kondo model. So we will cut across the middle. Okay, and this is the Schmidt decomposition. So the we arrange according largest to smallest. So we take the difference between the largest and the next largest eigenvalue. that is the Schmidt gap. Okay, and our handle for doing the phase transition is this K, which we call the RKKY coupling. Okay, so this is an artificial RKKY, and the other J dashes are the condo. Okay, so we see that after the phase transition, these values become degenerate. Okay, while all the other eigenvalues have a peak. Okay, so this, maybe I just elaborate 1 minute on this thing. This is a beautiful thing which is seen almost in any second order quantum phase transition, that the first and the second, though sometimes these may be degenerate, there may be more than, they come together, this Y, okay, and at one of the phases, and then this log n entropy that is contributed by all these others. Okay, the other Schmidt values also come in exactly at that point. They have a peak. This is usually much lower amplitude. So if you were to draw everything, the picture would always be a big Y and many humps at the of the entire spectrum. Okay, so this is seen in almost everything we have checked. Okay, so in this case, so particularly if you draw, then just take just first two Schmidt values. Okay, you see, by definition we are doing much less than entanglement here, because entanglement is related to all those Schmidt values. Okay, the logarithm comes from all those other humps. Okay, we are just taking the first two. Okay, so it's motivated by entanglement spectrum, but it is much less than, it's just lambda 1 minus lambda 2. Yeah, you can take, yeah. So, but you take difference between two Renyi entropies. Yeah, so yeah, you can. Yeah, you can consider it as a difference between two Renyi entropies. Yeah, so there may be, it may be related to entanglement also, but I don't know of any proof that this is an entanglement monotone or for pure states. It might be Renyi entropies are. Yeah. Okay. Anyway, so it starts one in the Kondo phase and goes to 0 in the RKKY phase. Okay, and interesting part is that its derivative diverges, and actually we expect it to scale. Okay, so also the Kondo length diverges. Here again, by what we mean by Kondo length is actually during the transition or after, in the RKKY regime especially, what to call the Kondo length. We always call the Kondo length as the entanglement healing length. Okay, that's our definition. Okay, so if we use that entanglement healing length does diverge at the phase transition. And then what is interesting, you can do finite size scaling, and one of the critical exponents, the exponent for the gap of the system, okay, the exponent for the length scale of the system, nu is known from previous CFT studies by Affleck and Ludwig. This is known to be 2. But this beta equal to 0.2 is a finding. Okay, so there was no order parameter before, and the Schmidt gap is an order parameter with this 0.2 exponent. Okay, whether how correct is 0.2, we don't know. It's only numerically up to certain. So it will be nice to see if theory can come up somehow with. We are making a cut at a very bad place for boundary CFT, right at the middle of the two impurities. So I don't know whether something can be done, but this is an exponent only known numerically so far. Okay, I would like to stress that Schmidt gap is an observable, of course, as we defined, because these are the eigenstates. Okay, but the eigenstates in general will be very non-local, so it is kind of a non-local observable. Okay, but it is an observable, so it's not like in general entanglement may not be observable. Having said that, negativity is also an observable, because you take all those eigenvalues, partially transpose them, you sum them up, is also an observable. Okay, it's an entanglement monotone which is also an observable, but also the Schmidt gap is an observable. But these are horrendous observables. There's no simplicity guaranteed. Okay, I believe that in case of simple models they become simple observables, but not. So anyway, the problem was that can we have a more local probe? Okay, so since time is going up, I'll try to speed up a little bit, yeah, just to convey the essence, but not so much the details. Okay, So we found a local, more or less, more local order parameter by going to study thermodynamics of quantum systems under Quenches, which is a very fertile field now. A lot of people, have kind of pioneered this field in various ways, but there are a couple of nice reviews. Okay, people try to define things like work, what is it? What is internal energy and these things from quantum states. Okay, it's a fertile field. We try to use some results from those. Okay. So what happens is that what happens when you quench a system? Okay, so a system is in some state. Okay, you want to quench means you want to turn on a coupling. Okay, you can think it physically as like you're bringing the thing close together to turn on the coupling. Okay, so you are actually doing some work on the system to turn on the coupling. Okay, so whenever you do a quench, you either do work on the system or the system does work on you. It depends on your quench and your initial state, but there is some energy input into the system. Okay, and then if you measure the system before, say you measure energy against, so to have a fixed energy, you can measure in energy basis before and after, then there will be a probability distribution of this work. Okay, because these are quantum states. Okay. Either the initial state will be eigenstate or the other one will be eigenstate, so there's no fixed work. Okay, so this is called work distribution. People can calculate various moments, but what we will be interested in is what is called irreversible work. Okay, why irreversible? What happens when you quench? It's a high energy closed system dynamics which starts. Okay, right? But of course, eventually the system will thermalize with its environment and come to its new ground state. Okay, that energy is lost to the environment. Okay, so this is the work which was lost. Okay, so you did some work to do the quench, to bring the thing together. Okay, at that high energy, the system is doing this non-equilibrium dynamics. After a long while, it relaxes, but this energy which escapes is not used. So it is called irreversible work. Okay, this is just a terminology. Maybe someone has a clever way of using it. That's a different thing. Okay, but essentially it is then a changed Hamiltonian and the original Hamiltonian and their difference in the same ground state. Okay, because when you do a quench, a sudden approximation, the state remains the same. So this difference of energy is the one which is released. And what we found is that you can show that this irreversible work is proportional to the spin-spin correlation functions of the impurities. Okay, the derivative. Okay, of the spin-spin. So if you and this derivative diverges at the yeah, it's the magnitude of your quench. Okay, so we do a slightly odd quantity where we take various delta k's, we divide by that. Okay, to get this this quantity. Okay, which diverges. Okay, this quantity, the problem is it doesn't diverge because this is multiplying a small change. Okay, so so anyway, so the point is that this simple thing, then the left and right impurity correlation turns out to be doing pretty much the same job as this Schmidt gap. Okay, and it has same kinds of scaling, while the irreversible work tilde as defined by us is diverges. Okay, I will skip over things. Okay, to show that it has the same scaling with this 0.2 and 2. Okay, so in retrospect, it is a long route to a simple thing. We found that the Schmidt gap is needed. Then we found that also the two impurity correlator is having the same exponent. Okay, but the two impurity correlator is very much measurable. Okay, in this artificial quantum dot scenarios, the measurement people actually do is a singlet triplet measurement. Okay, a triplet in two dots cannot come to one dot when you lower exponent, but the singlet can come. So essentially, what you do is a singlet triplet measurement. Okay, so you measure the swap operator of two spins. Yeah, So this is why you can also do all these Renyi entropy things with spin chains using the singlet triplet measurement. Okay? But anyway, the point is that you can measure this the scaling of that. If you have two quantum dots with their respective paths, you could measure the singlet fraction and see the scaling. And it will also have this interpretation, this irreversible work, a derivative of it. Okay. I will skip over these things because I'm nearly time. Yeah. So let me just tell you about some Quench jam is very similar to the one before. Is this the other way around? Okay. So previously we thought how to make a e-bit of entanglement, like almost an e-bit of entanglement into distance spins. Now we have the scenario of the two impurity condo model, and we do a quench here, okay, and see the time dynamics. Okay. So time dynamics of the entanglement, you can take the time dynamics of the Schmidt values, okay, so the entanglement spectrum, and we see what is interesting is that if we make the coupling such that the cloud covers the whole chain, then we get very nice periodic oscillations, okay, and these oscillations also could be of the Schmidt gap, but these are the individual Schmidt values, okay. I have not taken the subtraction here, but yeah. So essentially, if you Fourier transform, you will see a peak at a certain value, and this is the condo temperature. Okay, so a thing which was a thermodynamic temperature thing has now come into the dynamics. Okay, and it's I'll tell you why it is expected. Okay, if you question or if I have time, I'll tell you a simpler way we understand these systems. Okay. So you can make this frequency independent of your quench, both of K1 and K2. Okay, it's actually independent of K1 anyway. For K2, it is independent only if you adjust this cloud length to touch the end of the channel. Okay, then you have this thing. But you see, this reversible dynamics is not like a Rabi oscillation. So it is connected to bats with J dashed. Okay, so it's in an environment that you are having this thing. Okay, so that is why it's separate, and one frequency. Okay, so it is the TK. Okay. Yeah, so that is again the picture of the same things, that you really have dynamics overlapping on each other, independent of lengths, J dashed, and everything. Okay, just depending on the condo temperature. Okay, so the frequency depends on the condo temperature. Okay. But when you have less than optimal cloud, you have some environment out of the system, then it is more dispersive. Okay. At the same time, there is still always a peak at the condo temperature. Okay. So it's just that instead of being a thermodynamic scale, it has become a non-equilibrium dynamics time scale. Okay. Yeah, I'll probably not spend much more. So that is more or less it. I should just thank my other collaborators also. So Pasquale, so before you, I put up a slide actually on reminiscing. Well, thinking good of him, praying for him. Okay, he's in a bad situation, but and got me into these impurity topics. The work has been done, 99% of it by Abul Fazal Bayat, who will probably visit this program in November. And then Henrik Johannesson, also, these three people have been, Pasquale, Henrik, and Abul have been the main thing, but we have collaborated with some other people, also with Ian Affleck's group on Karin Lehur on the two-channel condo. I didn't go into that now. And also with Gabriel De Chiara and others on the thermodynamics. I didn't go into that either. Yeah. Okay, thank you.
I have somewhat historical but realistic question.
Yeah.
There is Sandro Papesco in Bristol. He works on these quantum engines. Is he related to your work?
No. This is kind of a different kind of that is more related to, well, is related to the fact that you try to define thermodynamic quantities for simple quantum systems from but I think he tries to do work on an atom. And many people look at the resource theory of that also, like Jonathan Oppenheim.
Who work on this silver engine.
Okay.
Probably naive, but
Yeah.
regarding the Schmidt gap,
Yeah.
we use trial wave functions and the variational principles.
Maybe, yeah, I don't know. I've never tried. Yeah, it's a good question because it is just the first two coefficients. Maybe it is possible. So it throws away a lot of the entropy, all those others. So we were surprised that this thing scales. You know that just the first two, Schmidt values, whereas the entropy is contributed by all these others. So maybe it is possible. Yeah. I don't know. Yeah, Sergey.
How should I think of this screening cloud in terms of spin?
Yeah.
Or is it just a topic
Okay, I think the best answer that I can give is this kind of ansatz that. Yeah. This is the best answer I can give, nothing better. So this is the impurity spin, okay. This is a block, okay, where you have an effective total spin, down, effective total spin up, okay, entangled, and then that entangled with other part of the, and this is real space structure, okay. So unlike, I think so I didn't hear your talk, but I heard David's talk. So you were going to the momentum modes essentially, and somewhere decoupling. This is of course in the line in the real space. Okay. I cannot give any better answer than that. Yeah.
similar picture for other spin models
like transverse Ising model with a J dashed, I don't know. So you require both the JZ and the J and the sigma plus sigma minus. Okay, you require for you will not see it in XY model, right? You require the interaction. The modes are this quadratic, these other terms, the C. So you require that. So you would require a high, I guess. As soon as you have a Heisenberg interaction with the impurity, or at least a ZZ interaction and still some off diagonal interactions, maybe you are flexible with other parts. You will probably see some cloud with the other. Yeah, Robert. Yeah.
Question about the two-channel condos.
Okay. Yeah.
So, I mean, can you use these effective spin chains and still be in that universality class?
Yeah, this is what we found. Yeah, that it is so one spin and two J dashes is they do mimic the thing well.
There's a non-trivial boundary contribution to the boundary.
Yeah, you have to add and subtract this.
Does that appear in the entanglement?
Yeah. So this was the content of our work, which I didn't say. Perhaps that is the most interesting work. It is already published this year, but essentially the boundary entropy becomes an entanglement entropy with the far. So what happens? So if I just summarize, what is our learning from that is that in the two-channel condo, this single spin with the cloud it forms the half ln2, and with the rest of the thing it forms the rest half ln2. It is this impurity is still entangled fully with both the things, okay, and it's that the entanglement is shared half within the cloud, half within the cloud, and since it's a closed system, this cannot have this thermodynamic, and it becomes entangled. The rest ln2 goes with the rest of the chain. Now extracting that was enormously difficult thing. This is why I didn't speak about that. So Erik Sorensen and Abol, they jointly, Arman myself, so it was very difficult to extract that entropy because there are many dimerization oscillations, not to say the least. There are many other terms to be eliminated. Yeah.
Being numerically sensitive to the channel.
Yeah, channel asymmetry was, I think, was pretty good. Yeah, it was not a problem. Yeah, not a major problem. But so that in what we maybe I can tell you more concretely about our contribution to that is that we found that the Schmidt gap as well as negativity could be order parameters with respect to the channel asymmetry. So exactly at one point you have a different value of these. You go and after that channel asymmetric point you have a transition in the negativity, and it scales with same exponents, 0.2 and 2.
We should probably move on to the coffee break. So let's
Yeah,
thank all of you.
thanks.